Hi everybody. So we're going to pick up on our discussion of the nature of light. Where we left off in class was that by the end of the 19th century, there was no doubt that light was an electromagnetic wave. So if you're a physics student coming through the ranks through the 1880s, 1890s, even 1870s, that's the dogma. There's no question of that. The question is now, how do we take this model of light and apply it to its interaction with matter? Okay, that was the next big step in physics. We understand light, we understand its electromagnetic phenomenon. Maxwell's equations describes electricity and magnetism beautifully. One of the most important outcomes is the origin of light. And so now we know light interacts with matter all the time. Okay, and it was around this time, ironically, when we are, if you will, we are so certain of the nature of light, especially with Hertz's prediction and production of radio waves, that we start seeing some cracks in this. Certain phenomena that just couldn't easily be explained. Of course, if you're a physicist at the time and you're going into research, that's exciting. That's where you can make your name if you crack that nut. So for many physicists, it was just in a matter of time. Give us enough time, we'll work out the details. Okay, turned out that wasn't the case. So what we're going to do over the next 3 or 4 tutorials is look at what the quote-unquote problems that arose at the end of the 19th century and into the early part of the 20th century. So the first thing we're going to focus on in this tutorial is something called black body radiation. A topic that had been very important in physics for a number of decades, and there was a major problem. And I'm going to try to explain the problem, but that's not the focus of this. I just want to give you a context for the solution and why the solution, while very simple, was unbelievably radical. Even for the person who came up with that, refused to believe its implications till the end of his life. All right, so let me explain the black body radiation. A fundamental aspect of physics is any object in the universe that has temperature must radiate energy, light. How it radiates that light depends on its temperature. So you see a few curves here. So let's take the first curve, the most prominent one. This is when you have a body that's about 5,000 degrees Kelvin. That's like the surface of the sun. The sun is very close to that temperature. What this graph looks at is relative intensity on the y-axis and wavelength. And you see that there is a peak wavelength where most of the energy occurs, and in this case it's in the visible part of the spectrum, and then it drops off exponentially towards the longer wavelengths, infrared, etc., and drops off very quickly, precipitously, at shorter wavelength, ultraviolet, X-rays, etc. So the sun is a major emitter of light, not so much in the other ones, but it certainly does. It's not zero. If you lower the temperature, you see that the curve shifts. That's 4,000 Kelvin and so on. So physicists wanted to explain this curve. These are experimental curves, okay? You can do, using a really cool device called a spectrometer, you can replicate these curves. So how do we model this with theory, classical theory? Well, the best we could come up with was a curve like this. All right, I think that's named after Raleigh. And then there was another equation which gave a curve kind of like this. But it was a different equation. And you can see, well, if I combine the two, I kind of replicate that. But that's not very satisfactory. That's kind of an ad hoc type of solution. We want to come up with something that's simpler and usually more elegant. But the problem was, no matter how hard physicists tried, they could not come up with an equation that gave us this curve. Again, based on not mathematics, but rather on physics principles. Okay, so along comes a guy named Max Planck. He was a young physicist in Germany. I believe the German government tasked him with trying to come up with more efficient light bulbs. And so that is tied in with, if you will, black body radiation. Well, I'll give you the solution in a second. So let me actually go back. So at the beginning of the 20th century, wave theory could not explain certain phenomena. Okay, so let's get into this. Intensity curve of the black body could not explain classical theory of light as an EM wave. No matter how we tried, how much we tried, could not be produced. So Planck was kind of desperate. He's looking for any equation that can be somehow tied in with the physics of light and matter. He borrows something from another physicist, an Austrian physicist, who is applying it to statistical mechanics, the physics of gas molecules. He misapplies the actual math, but he comes up with a solution that works. In fact, this is not part of the curriculum. This is not in your reference tables, but I thought it's worth seeing. It's this equation right here. This is Planck's equation that can replicate any one of these curves based on temperature. Okay, so the average energy of a black body follows this. And we'll just look at that carefully for a second. Here is the exponential part, the e to the hf over kt. K is a constant, h is a constant. H will become very prominent in a minute. K is something that comes up later. Okay, and so there's something unbelievably radical in this equation that Planck and his peers recognized. And it's this part right here. Whoops, let me go back here. And it's not immediately, obviously, mathematically, but I'm going to exploit that right now. And if you don't make the connection between what I'm saying, which is the important thing in this equation, that's not a big deal. Okay, I don't want you to focus on that. Basically, what Planck's solution implies, I shouldn't even say implies, it's fairly explicit, is that in order to produce this curve and therefore explain blackbody radiation, which is a feature of all of nature, not just light bulbs, is that light is emitted as tiny bundles of pure energy called quanta, the plural of quantum. Nowadays we call them photons. Okay, and this is literally at the turn of this century. So let's back up for a second. Let's look at the classical version of a wave very schematically. If let's say I shine a red laser for a fraction of a second, and we want to model that laser schematically, we would call it a classic wave, where it might look something like this. Okay, and what is this telling us? Well, there's a certain number of wavelengths. Well, that is determined by how long I show in the laser. There is a certain amplitude to those waves, and that amplitude, of course, goes towards the energy, right? The brightness. The brighter the laser, the bigger the amplitude. Of course, there is a particular wavelength and a particular frequency. The point is, it's a continuous source of flowing energy with a particular amplitude and frequency reflecting various properties. Planck is saying, no. If you're going to explain this curve, you have to, in a sense, treat light as discrete little bundles or particles, however you want to look at it, of energy packets, a quantum. So that we call a photon, but for right now, let's understand it as a quantum. And he's saying that has a discrete, and today you'd call it digital. This would be analog. This would be akin to being digital. Okay? It's not continuous. It comes in little increments. If you add up all the increments, you get the overall energy. But he's saying, and this is where this equation comes in, that each quantum of energy each quantum has an energy that is dependent on not the amplitude, because those little quanta don't have amplitude, but rather under frequency. Or put another way, you can look at it this way, wavelength. Because we know wavelength and frequency go hand in hand. All right, and he comes up with a very simple equation. He's saying the energy of one of those quanta, well, I'm going to put a P here for photon, because we use the modern term, is simply equal to h times f. Or, if we use the wave equation, h still stays there, we can say the speed of light, because that's how fast a wave moves, divided by its wavelength. Okay? So, if we're to make this, we see E and F are directly proportional. It's a very simple relationship. Well, in order to tie them together, we need a constant, and that's what the H is. And H represents one of the most important numbers, the most important number of all at the universe at the small scale, the quantum scale, and that's Planck's constant. Okay? And if you go to your funny reference tables, there is the SI, the metric value, which is often used, 6.63 times 10 to the negative 34. So it's an exceedingly small value. In fact, we're going to do an experiment where we're going to come up with something close to that value. And it has actually very interesting units called joule seconds. I don't have time to go into it, but a joule second is actually a measure of something called action. And it turns out action is a pretty important thing at many scales. Okay, if you go to the reference tables, it's sometimes very convenient to not look in terms of joules, but rather in terms of electron volts. So I think the value in your reference tables is 4.14 times 10 to the negative 15th. Sorry. And I'm getting that value simply by taking the joule part and converting it to electron volts using that conversion of 1.6 times 10 to the negative 19th. Okay, so we'll see that later. So that can be really convenient when our energies are expressed in electron volts rather than joules. Okay, so again, this equation comes out of this is a small part of that. It implies that light is quantized. It comes in discrete amounts, kind of like charge. We've seen that with charge. You can only have certain amounts of charge. You can add them up to get a bigger value, but there are certain charges that just aren't allowed. What Planck is saying, for a given frequency, certain energies are not allowed. That's quantized. Okay, so let's do some simple examples. So what is the energy of yellow light if the typical frequency of yellow light, of course there is a spectrum of that, or I should say, a band of that. If it's 5 times 10 to the 14th, so very simple, E equals HF, and if I gave wavelength instead of that, we just use HC over lambda, 6.63, right, joules seconds, times 5.10 times 10 to the 14th hertz. Okay, and you can see the hertz and the seconds are going to cancel out, and we get about 3.4 times 10 to the negative 19th. There's that exponent once again. That's not a coincidence. Joules. And if we ask how many electron volts it is, because that's the more proper unit at this scale, we just do 3.4 times 10 to the negative 19th divided by, that's joules, 1.6 times 10 to the negative 19th joules per electron volt, and we get around 2. And it's not exactly, but it's close enough. So we've got about 2 electron volts is 1 photon of yellow. So if we go back to this very simple diagram, right, that's the energy of that little photon if it was yellow. So I'm going to add another equation at the bottom here. It's not in reference tables. So if I want the total energy of a particular beam of light, if you will, again, if I shine the laser on for a half a second, I'm going to get gazillions of photons. Well, that beam of light has a total energy, which is simply equal to the number of photons times the energy of 1 photon. And of course, that simply becomes NHF, okay, or NCH over lambda. So we can introduce integers now, which is an important feature of any quantum effect that is not a feature of anything analog. So I could say, what if I want 1 joule of light, of yellow light from, let's say, a pure source, a laser source? Well, I would just take the 3.4 times 10 to the negative 19th joule, I'm sorry, take that back. I would say the total energy, 1 joule, equals N, the number of photons, times the energy of 1 photon. You can work out the math, but that's going to give us around, the reciprocal of this, around 10 to the 18th photons. So you need about 1,000,000 trillion photons to just get 1 measly joule of light. But that's beside the point. To finish up before we pick up on the next feature is that what was so radical about this and why Planck really had a hard time accepting the implications of his equation to solve a fairly mundane problem is that he is taking what he grew up on, the whole generation grew up on, as a classical idea of wave, and he's saying, no, that model does not work. It may work for a bunch of other phenomena. It does not work for this. And if you're somebody just starting physics, you're a new generation, you don't have these preconceived notions, you're going to say, whoa, that's pretty cool. It's hard to explain why this equation can't be valid if it explains the data. And the whole new generation really didn't have as much problem as Planck did, but it's the beginning. And we will now look into further phenomena that just bolster this idea that in certain situations you have to treat light as a quantum, a bundle of energy or a particle.